close my email first because it keeps popping up. Okay, so this just talks about the ventilation and air conditioning, guys, for this building. A couple of things. Every building you guys are in, are you guys okay? Hot? every building, every building that you're going to encounter, it's going to have three mechanical system. You're going to have a heating system to heat the building. You're going to have a cooling system to cool the building, and coupled with the heating cooling, you're going to have some type of ventilation system so you can maintain a certain you have to certain air exchange between the inside, outside in the building, so the mold can't grow inside your house or your building. So that's a big deal. Air exchange, they call it. So a couple of things that we're going to talk about, guys, is ventilator circuits. For us, being electrical guys, we care mainly about powering these equipment and controlling them. How to size the air handling unit for the building is beyond the scope of your expertise at this time. We can send you to a different program to learn that. So that's what determining the heating control for that equipment, if it's a heating equipment. Air conditioning is a big deal when we use with the chillers. So the few things that we're going to talk about, guys, is here, in particular one, exhausting the air out of the building or bringing air into the building, and cooling the air. So this chapter talks about cooling the air and exhausting the air and cleaning the air. Not the heat yet. I shared with you this document there, guys, that gives you the cooling in the system, and they're very complicated. This one is really easier. So we have ventilation units. These are your exhaust fans. In the building that we have, Chris, we have 5 or 4 exhaust fans on the roof. These are supposed to have some type of air exchange, exhaust the fumes out of the building, or air exchange between the inside and outside the building for pressurization as well as for quality of the air inside the building. A couple of description, guys, of the housing and the metal and all this stuff. When we do our tours, you're going to go see these big steel boxes sitting on the roof to exhaust the air out of that building. So that's what they're talking about. Who cares what they do and what size are they? Are they 15 horsepower, 5 horsepower? A lot of people, your job is not to size them 15 or 5. That's the job of the electrical engineers. Our job, they're 5 or 15 horsepower on the roof. What's my job? Do 2 things for them. Number 1, provide a feeder for them. And number 2, provide a fuse disconnect to power them. Most of the time, guys, even control them is beyond our expertise because it's tied to the whole heating, cooling, and ventilation of the whole building. So most of the time, we provide a feeder to feed them and a fuse disconnect or a circuit breaker to protect them. So that's what they're talking about. And this talks about how they house them and the housing and so forth. Noise is a big deal, but we really don't get involved in sizing these in any way, shape, or form. We don't. So I don't want to spend. Here's how they look like, your exhaust fans. You guys have, Chris, I will emphasize in this area right here. So I can't remember where, I don't know. Let's just come from this area. Here's my disconnect right here, and I'm bringing it all the way to the overcam protection device inside this panel. So here's where my interface with this unit is. Bringing a feeder into the disconnect, which could be fused or non-fused disconnect, and in turn feeding this blower or fan to feed the whole building, to feed the exhaust fan. That's my interface. This, most of the time, this one, guys, comes with the equipment, a disconnect with the equipment. Otherwise, you have to provide the disconnect right next to the air handling unit. An overcurrent protection device, overcurrent protection device, and a feeder. And Nick, if I tell you this baby here is running at 15 horsepower, 480 volt system, can you size the feeder and the overcurrent protection device for it? If you can't, ask for a refund from Dunwoody right now. Everybody guys know, if I give you a 15 horsepower 480 system and I give you and I want you to size the feeder and the conduit and the overcurrent protection device, everybody knows how to do that? Otherwise, you're going to go to Chad Kearney's YouTube channel, review a couple of these. So that's the only thing that you need to know. Why it's 15, not 25, beyond your scope. Okay, it talks about, then we have ventilation exhaust fans. Their job, again, guys, our job is always to bring the power to the equipment from a panel. That's the only job that you have to worry about. You have to have a disconnect for these equipment because they're mechanical equipment. What do? Is they circulate the air, guys, from one point to another. you grab the air here, and you exhaust it down. When we go to Allianz, right here, you guys are going to see a bunch of these unit exhaust fan on a roof in different locations, so they can exhaust the air. The thing that's not clear in my mind, not clear in the mind of a lot of engineers, guys, maybe, they interface these with the whole cooling, heating, ventilation system. So they run them if they want to bring. It's really interesting to learn mechanically how they do it. You have to maintain pressure inside the building and outside, inside the building, certain pressure, guys, pressurize the building. So you have to exhaust certain amount of air and bring fresh air, certain amount of air, so the mold cannot grow in your building. Fresh air. So they have an air exchange. I don't know if they use them as part of their exchange or not, but that's for our mechanical friends to decide. Electrically speaking, you're going to have a disconnect right next to the equipment if it's not there, and you're going to have an overcome protection device and a feeder. An overcome protection device and a feeder. The rule of thumb for mechanical equipment, Tau, is always to have a disconnect right next to the equipment. There's exception for this where the disconnect can be out of sight, but that's the exception, not the rule. That's the exception. If you cannot put the disconnect next to the equipment because of hazard, because of whatever, then you put it somewhere else. And that exception is very strict. So the rule is disconnect right next to the equipment. So keep this in mind. They have 4 or 5, 6 ventilation rooftop units, guys. And this is how they have a mechanical panel here. This is the project that you guys are looking at right in here. We have a mechanical panel that feed these 6 rooftop units. Each one of these is feeding a fan. So you can imagine. And my job and your job would be to provide the overcome protection device right in here, and a controller to be able to control them with interface. So I have my controller here, my overcome protection device for this equipment right in here. Minimum will be start-stop. Most of these guys will interface with the heating cooling system in the building. So your job, Tao, my friend, being you working at Hunt Electric, probably will be providing all these control enclosures as well as the gutterway. So this is a really nice way of bringing a gutterway. What I like about this project, guys, it's the project that you're having right here is made from an electrician point of view. Look how they did the feeders. You have two ways of bringing the feeders out from this building, from this panel, Chris. You can bring the feeders out individual conduits, right? Every individual conduit comes directly to the panel and moves. Or what they did is they have a gutter, extend the panel, and from the gutter they basically tap into the gutter to feed all these equipment. So if you are working for electrical contractors, really pay attention to this. This is a really nice system. What's the alternative again? Is bringing all these conduit directly to the panel. But that's it. So my job and your job is to size the mechanical panel, bring the feeder to the mechanical. This is feeder to the mechanical panel, and take the feeders out of the mechanical panel into that mechanical equipment and size them accordingly. And I have no doubt that all of you guys will be able to size it. Why? Because they're horsepower at a certain voltage. NEMA, this is your NEMA. NEMA 0 through 9, I believe. Do we know how to size a NEMA? No problem. How do you size a NEMA? Based on the voltage and the horsepower. We have a schedule that we give you guys. DeWalt is a great resource, and you can size the NEMA for it. Overcome protection device, no problem. If it's, for example, if it's inverse type circuit breaker multiplied by full load current from NEC, right? NEMA based on the voltage and the horsepower. What else do we need? Conductor. The conductor here, 1.25 times the full load current from NEC. Overload, you size it 1.15 to 1.25 based on the characteristics of that fan. Any question, guys, about this? That's what you're interfacing it. How it works, what it does do, the mechanical equipment. Really nice to read the book and read how they work, but the rest is history. With the mechanical equipment comes all these data. This is, guys, from Article 440. Very, very important data. I'm going to highlight 2 things that you cannot live without when you size your equipment. Number 1 that you cannot live without is called, this one, please highlight it. It's called minimum circuit ampacity. Minimum circuit ampacity. This guy is printed on the nameplate of your equipment. Minimum circuit ampacity, and this is your size conductor. And we did that one conductors. You grab the minimum circuit ampacity amp-wise, and you size your conductor, no question asked. The second very important thing is maximum overcurrent protection device. Maximum overcurrent protection device. This one you size the fuse or circuit breaker, no question asked. These are printed at the name of these mechanical HVAC equipment. This mainly for chillers, guys. This is mainly for chillers, compressors, not fans. These are typically for anything that has a hermetic motors, compressor, some type of a compressing system coupled with the motor. That's how they do them. Article 440, HVAC. This is the cooling part. Any question, guys, about these are the most important two things out of the whole deal here. Out of the whole deal. The second three, guys, the manufacturer, Chris. So these you have to know. If you deal with chillers and compressors and so forth, and HVAC and air conditioning, you have to know these two. The rest of them, good to know, comes with the manufacturer. For example, the continuous maximum over continuous current, the manufacturers, guys, run the equipment, the compressor with the motor, run them at a certain value before if it reach after this maximum, the equipment starts smoking. That's the highest amount of current that can come out of this chiller or the AC unit before the smoke starts coming out of it. Careless for the most part about it. Rated load amp and branch circuit selection current. These are equivalent to the full load current in the NEC code book. Equivalent to the full load current. So Chris, if you don't find these two values, then you use the full load current and you size based on the full load current. If you don't have them for the chillers, most likely you're going to find the MC and the fuse size for chillers right into them. So you grab these sizes, size your conductors.
Just a question on most of these, like the chillers, they don't compress anything. They're blowing fans. So you're at 430 for most of your units.
Chillers, no, you have a compressor with them. The air handling unit. The air handling unit. They have to have some coolant system. They have to chill the water. You have to have the coolant. So part of the whole cooling process.
Well, on the diagram we looked at, all we saw was water. We didn't see refrigerant.
Yeah, you didn't see the whole picture though. There's a whole lot of things that you're chilling. You have to go through a refrigerating cycle and chill through a condensing.
So if it's using refrigerant, then you go to the AC.
You got it.
And if you're using the strictly motor, not.
You got it.
You go to 430.
You got it. Absolutely.
Okay.
The divide between using 430 and 440, guys, if you have a compressor that compresses some type of refrigerant as part of the equipment, and mostly chillers will have that one, AC units. Rooftop units too have them. They call them rooftop units. If it's strictly just a fan, a motor, no compressor or no refrigerant in it, no compressor to compressor refrigerant, then you go to 430. Does that make sense? Everybody can see that divider between a motor standalone only, just a horsepower, versus a motor coupled with a compressor. So these are, guys, the most important things. This is just explanation about how these units, like maximum overcurrent protection device, they run them. You don't need to know about that one. And also, it's not on the nameplate. Usually, you have to find this maximum overcurrent protection device on the data. Rated load amps, the way they do the rated load amps, the only thing I want you guys to highlight is this one. They take the largest amount of current that the equipment can handle can suck before it starts smoking. As it compresses the refrigerant and circulate and do all this refrigerant cycle, the largest amount of current before it starts smoking, right? And then they take 64% of it, and that's what they call it, the rated load amps. 64% of the largest current before smoke starts coming out of it, or blow up or whatever, and they call this as rated load amps. You don't have to know that, other than for Chad and the test. In real life, you're going to have this one, rated load amps, right on the nameplate, Branch circuit selection current, guys. Branch circuit selection current, because here's the key point. because the motors are tied directly with a compressor, and they call them parametric refrigerant. You have some type of refrigerant, compressor motor. This is compressor with a motor tied together with a refrigeration cycle, some type of refrigeration cycle. Because of this, guys, they have to have something called branch circuit selection current, which is equivalent to the rated load amps, but it takes into consideration all the system working together. So as far as you're concerned, branch circuit selection current or rated load amps, one of them will be on the nameplate. Typically, the rated load amps. They're equivalent. They are the same. As you can see, at least this will be the value. At least this will be the value. So sometimes, Chris, the rated load amps is different than the branch circuit selection current because how the equipment work with together with the refrigerant. If you read through it, guys, they take the pressure, the temperature of refrigerant, how it works. At certain temperature pressure, the motor can work harder or less hard or more hard. So they come up with this branch circuit selection current. All what you need to do, it's minimum. This have to be the rated load amps. So if it's higher than rated load amps, you have to choose the largest of the two. The largest of the two. Any comments, any questions? The largest of the branch circuit or the rated load amps. Who cares? On these refrigerant, guys, we always have the rated load amps printed on them. Okay, minimum circuit ampacity. We talked about this one, guys. This is where you're going to size conductors. You're going to size your conductors. That's done deal. No thing. If you don't have this value, if you don't have this minimum circuit ampacity, if you don't have it, then you have to treat it, Chris, like any other motor. You take 125 like a motor, but instead of going to the code and get the full load current, like we did in our examples before when we did the HVAC example, you guys have done it. You're going to multiply this one by the branch circuit selection current or the loaded or rated load amps, whichever is larger. So take this. Suppose the manufacturer told me the rated load amps was 100 amp, and the branch circuit selection current was 150 amp. And they did not give me the minimum circuit ampacity. They did not give me the minimum circuit ampacity. So I'm going to choose the largest. I'm going to take 1.25 multiplied by 150 amp. So what's 120 times 100?
This is for a refrigerant.
This is, yes. This is for anything that have refrigerant going.
Because earlier you said they take that into consideration, so you don't need to do the 1.5.
You don't have to do it if you get the minimum circuit ampacity. You do it if you do not have the minimum circuit ampacity. So this, if you do the math on this, guys, you're going to end up 188. This is 188 amps. Cool? 188 amps. That's how you do the math. Guess what? If you end up working for a manufacturer of this type of equipment, you know what they do? You will be doing all this, and you, Chris, will be putting this minimum circuit ampacity at 188. So that's how they come up with the minimum circuit ampacity themselves. So if it's not thrown on a nameplate for you, which most likely 99% will be, this is how you calculate it. And if you're working for the manufacturer, how do the manufacturer come up with this magic number? That's exactly how they do it. They take the rated load amps, multiplied by 1.25 like any other mechanical equipment. And then, obviously, if you have other equipment, relays, whatever, you add the full load amps. Like remember, if we guys have a feeder feeding multiple motors, we add 1.25 times the largest plus all the full load current for all other motors. Okay, overcurrent protection device. Overcurrent protection device, Chris, we did these calculations. If it's not given, first of all, overcurrent protection device max. If you don't have the maximum overcurrent protection device, if you don't have it, this is how you calculate it. You're going to go, the range is 1.75 all the way to 2.25 times full load, rated full load amps. Rated full load, rated load current. Rated load current. Rated load current. If you guys go to Article 430, 440, which you have done before, and you did the sizing for me. I asked you to size based on 1.75. If you read the article, it says size based 1.75, but if it doesn't start, if your equipment does not start, then you're allowed to go to 2.25. Cool? So your start point is 1.75. If the equipment does not start because it's a low fuse, you can go up to 225. In either case, when we did the HVAC equipment, which you guys will be tested on next week on this equipment, we said when you do the math, if it's not a standard, you go to the bar, get drunk, and get mad, one option. And the other option is custom design a fuse. And the third more logical option is to go down to the next standard. Any question? We did calculation in these guys. This is just a quick reminder of what you need to do. Always start with 1.75 unless you know. And then these are the coils that they bring the cold and the hot guys coming out of them, and you throw, depending where this, they talk, and I don't want to open even this can of worms. They talk about coils, guys. Mechanical coils. You can use mechanical coils with the compressor, with the condenser, with the evaporator. It's a coil is just a pipe. Imagine a lubo pipe, and you push through this pipe hot water or cold water or refrigerant, and throw air through a blower right through the coil. This coil could be in the air handling unit. That would be an evaporator. Could be the coil. Could be in the condenser. In the condenser, or it could be anywhere else. As a matter of fact, it's just bringing some type of refrigerant or hot or cold refrigerant into it, and you blowing air right through it to get you through what? Through a fan. You have to have a fan. So the mechanical contract to the mechanical contractor, this coil is, you know what this coil is for, like us. This is like sizing almost a lighting fixture. And adding big deal. This is like what am I going to say? Almost a lighting panel for them. Just coming with an actual size for this coil. They call it coil. So just be aware of that one. Overload. You guys have done this overload with Chad. Same thing. If you guys are very familiar with this, the overload can go from this value to this value multiplied by the full load amp on the name plate. So this is review of what we have done, the nameplate. Chris, if you have no idea what type of equipment you have, what do you start? Most conservative, you go 115. You go 115. When do you use 115 and when do you use 125 for motors? You guys remember that rule? If your temperature rise is 40, temperature rise of not over 40, or the service factor, they don't have the service factor here, or the service factor is 115 or larger, then you use 125. All other options use 115. That's directly, guys, from Article 430 for motors. HVAC equipment have their own control, overload protected by the manufacturer. They use almost the same rules. Any question, guys, about the overload? In other part of the world or other location, guys, they might have one device that provide overload and overcurrent protection device. So if you have one device that gets you overload and overcurrent protection, then you size this by 1.25. So typically we don't encounter this here. That's mechanical. Then they get into the belt span and the deflection, and I'm going to leave this to my friends. The deflection and the belt span, guys, that they couple the equipments together, the fan to the motor, is unreal. There's a lot of calculation. If you want more information about the V-belt right here, and DeWalt has tons and tons of sizing a V-belt for a piece of equipment. Mostly we don't get involved in this one, Tal. It's a mechanical specification. Mechanical engineers will specify the V-belt. This is when you add a load to a motor, guys, you can either mechanically, physically couple the load, like the fan, directly into the motor. You couple them together, or you tie them through a belt, right? So then the belt moves, it moves that van. So there's so many ways of doing it. Advantage, disadvantage, what the load. I'm going to leave this to your mechanical engineers to figure it out. As far as we're concerned, just be aware Um, Especially if you're doing, none of you guys is electrician. If you're maintaining electrical, or I mean, none of you will, for the most part, work as electrician. If you work as electrician, this will be one of the most, one of the reasons why motors will fail. If the belt is not tight enough, then it puts a drag on the bearing over here. It damages the bearing. So that becomes, if you're doing maintenance in a building, knowing the mechanical side of the equipment is unreal, because it's gonna create, if that V bolt is not sized right, it's gonna create a drag onto your motor, and it's gonna cause the overload protection device to trip prematurely or constantly. So for overload, because it's working harder than it should. So just be aware of that one. Liquid chillers. There are two types of chillers: liquid chillers and the non-liquid chillers. We're not going to go to the other type of chilling. Liquid chillers, you guys are looking at this. You bring a refrigerant, some type of refrigerant compressor, and you chill the water. After you chill the water, you circulate the chilled water directly into an air handling unit. That's the top part, guys. When you chill the water and you circulate it into the air handling unit, you get yourself you get yourself cold, right? Where's my here? So this is what you're looking at right here. So if you circulate, this is my chillers. Oh no! Did you do something to mine, Chris? Here. Okay, I just want to draw this one here, guys. And coming out of, oh my buddy, why does it want you? Okay, doesn't want to do it. But you can see that you're chilling the water, and you're bringing the water out here into these coils inside the air handling unit, and you're blowing air through these coils to get your cold air, and then the water becomes hot, and you circulate the water back bring the water back. You bring the water back into the chiller, chill the water again, and keep circulating it. So that's what the whole circulating business. That's cycle number one. Cycle number two, guys, another water system is going and taking the heat from inside the building and dumping it into Mother Earth, throwing it to Mother Earth. So I'm not going to go even. So these are two different cycles of water. If you can imagine, one circle is giving you, one circle is allowing you to circulate the chilled water into the building. The other circle is to take the heat out of the chillers, take them outdoor to Mother Earth, to a cooling tower, huge blowers blowing air right through the coil, taking the heat that you collected from the building and giving it back to the Lord outside. So, and all these is happening inside the building with a compressor. If we have a chance one time, we used to bring a mechanical speaker to talk about the whole system from a mechanical point of view. If you're working for engineering firms, the first thing I would do when you start working on a chiller, have a good friend, mechanical engineer, take a picture like this and let him explain to you how the whole system is put together and how it works. It's really interesting, intriguing. Then you can appreciate it when you assign all these circulating pumps and all this good stuff. You understand it fully. Okay, so that's what I want to say about the chiller. Connecting them. Okay, here's how it looks. You guys walked when we go to Allianz, you're going to walk, which is not next week, the week after. You're going to walk around big, huge, it's like a generator almost, chillers. These are where you chill the water and you circulate the water into your building. I think they have 4 of them. So I want you guys to look at, as you walk through, just to have an idea, an appreciation of the whole system. With a VFD control right here, as you can see, directly VFD control most of the time. VFD control, disconnect VFD control right in here, and then you come and you size the overcome protection device coming for the building. Our interface electrically with it is coming right here, bringing the feeder into a VFD, provided most 99%, guys, by the owner, and powering this creature. And the rest of it is bringing the cold water, keep chilling the water and circulating that water through pumps. You can see next to these will be multiple pumps sitting there and circulating these chilled water all through the air handling unit or units, and bringing it back as a hot water chiller again, and keep doing the whole cycle. The reason why the code treat this type, that's exactly what the answer for you, Chris. The reason why the code guys treat the chiller motors, the compressors that come with the chiller motor separately, is because they call them hermetically sealed compressors, because what they do is they use some of this cold water and they chill the compressor motor itself. They chill it. So it's not naturally cooled. It's almost you force to cool it. So here's a good example where you bring some type of water or something to cool the motor. Your motor right here is being cooled through the process. Who cares? The problem is, who cares if I'm cooling my motor? If you have some type of a forced cooling system into your machine, guys, you can overload your equipment. You can overload. I can make a 15 horsepower motor give me work a lot harder, give me a lot of power if I can chill it. Force it. It's not just by the air being around it. So long story short, because of this phenomenon, the code treat them as put them all in 440 versus putting them in 430. If it was a fan, it would be in 430, treated like a motor. So they treat them separately because of this phenomenon. They are forced, they have some type of forced cooling for them. The windings themselves in these motors that run the compressors, they're cooled through the process. You can't do that in a fan, can you? I mean, a fan is...
Well, the fan blows air on the motor, gives it much more.
Yeah, that's also another cooling, but this is much better. You have some type of liquid cooling. Okay, they have, in the project that we have, guys, they have something called Reciprocation Units. The Reciprocation Units is supposed to, for the equipments that you have, I think I have the this one only for manufacturers, Reciprocation Units for the most part. If you have a process where you have a lot of contamination, it's supposed to take the contaminated air around the machines, right? Remove the oil mist and the smoke and the odor, return a clean air into the building. Imagine self-contained unit that you put it right next to that machine that makes smoke, and as you cut all these steel and sort of thing, so you suck the air, clean the air that's coming out of this machine, right, and circulate it back into the building. So it's basically like a cleaning ventilation, specific ventilation for equipment. That you can find something like this in manufacturing floors. You're not going to find this one in an office. You're not going to have a lot of odor and a lot of mist, oil mist, and smoke coming in an office. That's going to be manufacturing floor. You put that machine right to suck the air out of the air around this machine, clean it, and dump it back into your system. Clean it, dump it back into your system. They also use some process of salvaging the oil to be reused to save. So where do you use it? Directly behind, above, or at the side of the machine. So I have a machine that's making all these noises. I can blow in this bad stuff. I can put that system to suck, take the air out, clean it, bring it back. It just makes the environment where people work is cleaner and safer. Manufacturing. The way they do it, this is just a couple of things, guys. The way they do them, they have something called ionization. They bring the air here. Here's air. They bring the air here, and there's something called ionization here. When they bring the air here, they charge it. They charge the air with positive, because that ionization, if you have a coil positively charged, it ionizes the air. It makes the air positive. If it makes it positive, it makes the air positive. The mist and the bad stuff in the air becomes positively charged. Then they shoot it right through these negatively charged plates, and guess where all this bad stuff is going to hit? Right in here, and so it cleans it by positively charged particles attract to negatively charged collectors or plates. Who cares? Out of this, you get clean air. That's all what we care. The rest is history. For us, what's our involvement with this, guys? Sizing the overcome protection device for it, the disconnect, as well as the feeder, and knowing a little bit how it works. So we have a bridge. Then what they do with them, guys, they have a bridge so you can rectify the AC to the DC. So the ionizers can work and ionize the system. It's a whole standalone system. Collector is flat metal plates that collect the particles. So that's a way of cleaning the air right next to the machines. We talked about bridges, guys. This is because in the power industry we don't have DC source. What they do is they grab a feeder from here to feed it. Say it's 100 amp, and let's just say two pole 100 amp, and you feed this equipment, right? And this equipment bridge this one down into, I don't know, I'm just gonna throw, say let's just say 200 volt. I might be completely out of whack DC. And then they charge the plate, positively charged plate, negatively charged, another plate, the ionizer, and they throw the air through them. They use a lot for this, guys, for printing and so forth too. There's a lot of ways of moving them. Okay, so that's basically to locally clean the air. The last one, guys, is a portable precipitator. You can use a portable ones. Does the same thing. You plug it into 120, clean the air, dump it, clean air. Dump it as a clean air. And I know I promised you until 10:30, but of course I lied to you. Okay, so that's what I have, guys. I just want to see if I missed any of my slides here. If you do me one little second here, library 12. I think we did most of it. Okay, so we got that fans, exhaust fan system, chillers, okay, compressors, this one, rectifiers. Then they have different systems, guys, that they can. Here's how it looks like, this baby. It sucks the whole bad air, clean it, bring it as a good air. Interesting, Chris. This is your values of build deflection. The engineers love this because it gives you that's how you size your builds for it. So because the reason why they do it, because these exhaust fans, I don't know if you guys can see right here, they're built driven. They have the motor is right here. They drive that fan through a build. They're not directly coupled together. They're build driven, and that's a whole lot of sizing and so forth. Okay, that's all what I have. Any question? If I want to summarize what we did, guys, today is Article 430, chillers, anything that has a compressor on it, you're going to treat it separately. You're going to have two very important values for chillers. You're going to have minimum circuit ambiguity and maximum overcurrent protection device. Based on these, you size the overcurrent protection device as well as a conductor going through a chiller. Most likely chillers, you guys were looking at these, in this day and age, almost all chillers have VFDs driven. VFDs can control speed them. By control speeding the compressor and so forth, they can precisely, and I hate to use precisely in front of Chris, precisely control the temperature in your room. So the more VFDs on your equipment you have, the better environment environment air control that you can have in your building, quality air in your building. My advice for all of you guys, especially the ones who work for engineering firms, always team up with the mechanical engineers, and the more you understand about their system, the better you will be as an electrical designer. It's not just how many pumps you have, and it's really nice to understand a few things about the system. We will never be designers, guys. I mean, unless you go and specialize in designing chillers. They have a whole lot of science about the refrigerant, pressure, and temperature, and all this good stuff. Yes, sir. Typically, if you have VFD equipment, is sized by the manufacturer of the equipment for a couple of reasons, guys. We can't get involved in it. My experience with them is mostly mechanically driven because they take into consideration, is it variable torque or constant torque? So now we don't talk a lot about torque, and we care less. electrically speaking. I don't care what that machine mechanically is doing. Well, I do, but that's so there's a lot of mechanical component in it. I'll show you. I usually don't touch on it, but there's a Color Hammer has a really nice. I'll show you later on where in their consulting manual they have a nice sheet that can size a VFD for you, and based on is it variable torque, constant torque, and of course the voltage and the horsepower and so forth. But you need to ask them, do we have a variable torque on this motor, or do you have a constant torque, a fan, constant torque moving on, variable bell torque? So there's a lot to it than just electrically speaking. So, but I can show you where in Color Hammer you do them. What we have done in the past, guys, is usually we say VFD, specify the voltage and the frequency, the voltage and the horsepower, and let the mechanical engineers get into the details. Any question? That's all what I have for you guys. We're set for the week. Tomorrow we're gonna have a speaker, guys, that talks about project management estimation. So just give you a heads up, and also looking for somebody to hire. So if anybody, if you're looking to work as an estimator, project manager, bring your resume tomorrow with you. Did you guys hear me? William and the ones who are not working. If you want to work as an estimator, project manager, bring your resume with you tomorrow. Paul is going to be here, and most likely he will be able to sit and talk to you, I'm sure, after his hour. So